Hello, chemists! This is Ms. Placino, and you are watching Lesson 3.1, an Introduction to the Periodic Table. Today, we're really just going to introduce the periodic table and discuss its organization and some basic pieces of information we can gain just from really the location of an element on the periodic table. Some goals for today's lesson: explain how Mendeleev's periodic table was arranged, understand the arrangement of the modern periodic table, recall general properties of metals, nonmetals, and metalloids. Understand the significance of isoelectronic stability. Don't panic if you haven't heard that term just yet. And predict the formation of ions. So lots packed into this introductory lesson. Let's get started. Okay, this person here is Dmitri Mendeleev, and he is credited with creating the first modern periodic table, and we're looking at 1869-ish, 1870-ish, depending on where you look. Mendeleev arranged elements by increasing atomic mass and similar properties. Now, hopefully it goes without saying that at this point in time, not all of the elements had been discovered, and basically what Mendeleev did was write down the known elements on like index cards, along with some of their properties, maybe like reactivity, density, appearance, ability to conduct electricity, so on and so forth. And while we didn't know atomic masses at this point in time, we didn't have the discovery of the proton and the neutron until well into the 1900s, there were relative masses. Like scientists knew that hydrogen was 16 times less massive than oxygen, for example, but there were no real numbers attached. It was all just relative masses to one another. So he started to arrange his periodic table according to increasing atomic mass, but he would leave gaps in the periodic table and kind of sometimes break that rule of increasing mass to keep elements with the same properties grouped together. He made really bold predictions about what the properties of missing elements would be. And initially, people in the scientific community were not very pleased with the fact that this one person thought that they could make guesses, basically, about what elements were missing and what their behavior and properties would be like. But history proved to be on Mendeleev's side. Eka aluminum, what we call gallium today, and ecosilicon, germanium, are two that Mendeleev was able to pretty accurately predict A, their presence, and B, some of their properties. So his periodic table was really a huge advancement in chemistry. This is Robert Mosley, and he was actually a student of Ernest Rutherford's. He arranged elements by increasing atomic number in 1913. So again, I don't think we have the proton discovered just yet, but we were able to look at the relative positive charge of the nucleus. He discovered that when you arrange elements according to increasing atomic number, you can observe what we call the periodic law. Basically, the properties of the elements are functions of their atomic numbers, and instead of just being like one single trend, as you like take a property and you graph it against the atomic number, you're going to see like these repeating patterns. Robert Mosley, unfortunately, his young life was cut short in World War I. He was shot down by friendly fire. His scientific accomplishments probably would have earned him a Nobel Prize, but those are not given out to people who are deceased. You have to be alive to receive it. So unfortunately, the scientific community was robbed of a really great mind way, way too soon. Let's talk about the organization of the modern periodic table. So hopefully this looks pretty familiar to you. You might see periodic tables where this is filled out all the way to the very end, this bottom row. More elements have been synthesized, so this is like a little bit of a dated periodic table. Technically, we're supposed to take that two-column pile of elements at the bottom of the table and shove them into the actual periodic table. For size reasons, we've gone ahead and left it just the way it is. We're going to focus on the S and P blocks of the periodic table. So hopefully you recall from last unit when we were talking about electron configuration that that's really just going to leave us with these two groups of elements. Groups are the vertical columns. So there are 18 groups in the periodic table. Sometimes you'll see them numbered a little bit differently. You'll see like a group A and group B elements, but typically you tend to see this 1 through 18 listing. That's the one that's in our reference table. Periods are the horizontal rows. And there are 7 periods in the periodic table, and to date they are completely filled out. When another element is synthesized, it's going to have to start a brand new period in the periodic table. So electrons that are the outermost orbit or shell are called our valence electrons. You may have heard this term before. Valence electrons are extremely important. These are the ones that are going to determine many of the chemical and physical properties of an element. It turns out that if you've got the same number of valence electrons, you probably have pretty similar chemical and physical properties. So we can use location on the periodic table to figure out how many valence electrons an atom should have. So we're going to look at sodium to start, element 11, and we're going to kind of revert to the Bohr model of the atom. Yes, I know it's not 100% accurate, but for what we're discussing in this unit and really future units, the Bohr model of the atom does a very good job. So we'll try to scale back and keep it a little more simple. All right, so there's sodium, and if you find it on the periodic table, it's in period 3 and group 1. The period tells us how many orbits or how many shells or energy levels, again, whatever you'd like to call them in the Bohr model, need to be present. It's in period 3, so we should have 1, 2, 3 orbits. The group number tells us the number of valence electrons. And as you can see in this Bohr model of sodium, it has just 1 valence electron. Let's do a little bit of practice with that. All right, so now we're in the practice problem section of your notes, and question 1 asks you to fill out the table using the location of each element on the periodic table. Let's take a look at barium, and we're going to determine the number of energy levels, again, according to the Bohr model, how many valence electrons are present, and if we kind of think back to a lesson a couple units ago, is this a metal, a nonmetal, or a metalloid? Don't worry if you've kind of forgotten that, we will revisit it actually right now. So you need your periodic table. Unless you've got all of the elements locations memorized, this is going to prove to be really helpful. So take a second, find barium on the periodic table. Oh, there it is. Okay, so barium, it is in period 6 and it is in group 2. So what does the period tell us? Yeah, that's number of energy levels. You kind of have a built-in check right there. You can look at the electron configuration. We'll zoom in a little bit. And you can count the number of energy levels. So we're predicting 6, 1, 2, 3, 4, 5, 6. Absolutely. The group tells us the number of valence electrons. And we would predict 2, and sure enough, there are 2. When it comes time for like the test in this unit, you're going to not have the opportunity to use your reference table. You'll be given a pretty stripped down version of the periodic table, just with things like atomic mass, atomic number, and atomic symbol. So you can use these little checks for the time being, but don't become too dependent on it. As far as whether barium is a metal, a nonmetal, or a metalloid, hopefully you remember about the staircase. The staircase separates metals from nonmetals. So everything to the left of the staircase is metallic. One major exception, hydrogen is a nonmetal. Everything to the right of the staircase is nonmetallic. And everything touching the staircase on 2 sides is a metalloid with one exception. So 2 sides on the staircase. Like carbon is just kind of touching that corner. That's not one. Silicon is. Aluminum is the exception. Aluminum, despite looking like it would be a metalloid because of the 2 sides touching, is a metal. And sometimes you see a little bit of debate whether polonium and actinium should be counted as a metalloid. I wouldn't stress too much about that. As long as you know that aluminum definitely isn't, I'm pretty happy. So let's go back to the practice problems and kind of finish filling that in. Okay, So we saw 6 energy levels, 2 valence electrons, and barium is a metal. Go ahead and, let's do bromine, Br. So pause the video, see if you can figure out bromine. We'll get started again in a moment. All right, bromine, number 35 on the periodic table. It is in period 4. So it should have 4 energy levels, and it's in group 17. Doesn't have 17 valence electrons, it has 7. You can just subtract the 10 from those. Metal, nonmetal, or metalloid. Well, bromine is very clearly to the right of the staircase. It doesn't have anything in contact with the staircase, so it is a nonmetal. All right, let's get back to the notes. I want to take a little time to talk about the formation of ions. If you recall, ions are atoms that have either lost or gained electrons and now have a charge. It turns out that having a complete set of valence electrons, or sometimes called an octet of electrons, is very stable. And we talk about stable in chemistry, we're usually referring to low energy. And molecules, atoms, etc., they tend to want to be in a low energy configuration. So if an atom can do something to lower its overall energy, it's usually going to take advantage of that. So we've got 4 models of 3 different atoms: sodium, neon, and fluorine. If we take a look at sodium, if it wants to get a complete valence shell of electrons, and it can do that either by gaining or losing electrons, what would probably be the easiest route to go? Well, hopefully we see the word octet, and we know that that means 8 electrons. In my valence shell right now, I have 1 electron. Do you think it's easier to try to gain 7 electrons? Or just lose that 1 electron? Yeah, it turns out that losing the 1 electron is much, much easier to do. So the sodium atom is thinking, of course not actually thinking, but it will behave in a way to get rid of that 1 electron. When it does that, it'll go from having an electron configuration of 2, 8, 1 to just 2, 8. It's now completed its valence shell. It'll become a positively charged ion. Sodium will go to sodium plus. If we skip over to fluorine, fluorine has an electron configuration of 2-7. It's got 7 electrons in its valence shell. Do you think it's easier to try to lose those 7 or gain 1? Hopefully you're thinking gaining 1 is going to be a lot easier. It might be able to steal an electron from a metal, and we'll take the fluorine atom. It's gained a negatively charged particle, an electron. So it now becomes F-, and it is also very stable. If we take a look at neon, it's got the electron configuration 2-8. Is there any reason for neon to gain or lose an electron? Well, no, not really. It already has that octet of electrons, that stable set of 8 electrons in its valence shell. There is no push for neon to gain or lose electrons. It's going to disrupt that stability. So neon and other members of group 18, the far right column, really don't tend to form ions at all, not under normal circumstances. So it's just going to remain neon. No ion is formed. Let's take a look at some practice problems and try this out. Okay, I want to take a look at these first 3, beryllium, iodine, and phosphorus. So let's go to the periodic table, and we'll just try to keep in mind Be, I, and P. We'll start with beryllium. And I'll erase some of my other stuff here just to make it a little bit cleaner. So beryllium is a metal. Right off the bat, that should tell you that beryllium is going to lose electrons. Given that beryllium has an electron configuration of 2-2, and we know it's got to lose, this is one of those cases where it won't end up with an octet of electrons. It will have technically a duet. We can't put 8 electrons in that first shell. So when beryllium forms an ion, it is most likely going to be a +2 ion. Let's go over to iodine. Iodine, element 53. Iodine is a group 17 nonmetal, so we know that it's going to gain electrons to complete its octet. Group 17 has 7 electrons in their valence shell. To get to 8, they've just got to pick up an electron. So iodine will tend to form a -1 ion. And the last one in that group was phosphorus. Phosphorus is a group 15 nonmetal. It is also going to gain electrons to complete its octet. So to get from 5 electrons up to 8 electrons in its valence shell, it's got to gain 3 electrons, so 3 negatively charged particles. So phosphorus will tend to form a -3 ion. So we'll see beryllium, and whether you want to write Be2+, or you just want to write like -1, doesn't especially matter to me. I'm going to keep it as we'd actually write it. I- phosphorus, phosphorus 3-. Technically, when you're writing ions, the numerical value comes before the charge. At this point in the game, if you flip it and you call it a +2 instead of a 2+ charge, I don't care. I'm happy that you got the correct numerical value and the correct charge. Go ahead and take care of aluminum and arsenic, and we will review in just a moment. All right, if you find aluminum on the periodic table, it is group 13. It is a metal, despite having 2 sides of its element box in contact with the staircase. Since it's a metal, it will lose electrons to complete its octet. It's in group 13. It's got 3 valence electrons. It will lose those 3 to form an aluminum 3+ ion. Arsenic is in group 15. Whoa. There we go. Group 15. So it is, but based on its location on the periodic table, it is a metalloid. So metalloids technically can gain or lose electrons to get to their complete octet. They'll do whatever's easiest. Arsenic with its 5 valence electrons, probably going to be easier to gain 3 electrons than it is to lose 5 of them. So in all likelihood, in most scenarios, we'll see arsenic with a charge of 3-. All right, keep practicing with that, and hopefully you're starting to get really confident with how to predict what the valence electron configuration will be. If you notice, all of these ions, now have the same configuration as a noble gas. This is what we call isoelectronic. It is very, very stable for an ion to have the same electron configuration as a noble gas. That stability comes from having a completed octet, and it's going to overall lower the energy of the ion. I want to finish up the lesson just by going over some general properties of elements. So based on the periodic table location, whether the element is a metal, a metalloid, or a nonmetal, you can make some general predictions about its properties. We just talked about one of them with ions. We're going to start at the bottom first. Metals are going to lose electrons to become cations. Nonmetals, the polar opposite. They're going to gain electrons to become anions. And as we discussed with arsenic, our metalloids, also called semimetals, can either gain or lose electrons depending on the environment. And really what we mean by that is if a metalloid is reacting with a metal, it tends to gain the electrons as the metal has to lose, and the opposite holds true if that metalloid is reacting with a nonmetal. Other properties of metals. They are ductile, meaning that you can either pull them or roll them into thin wires. They're also malleable. If you were to take a chunk of metal, like something like gold, for example, gold's extremely malleable, you can hammer it into a thin sheet. Nonmetals, on the other hand, are not. We call them brittle. If you were to take a chunk of sulfur, a yellow solid, and smash it with a hammer, you're going to end up with a bunch of yellow dust. With our metalloids, they're usually too brittle for metallic applications. So it would be difficult to make a wire out of a metalloid. They tend to start to flake apart a little bit, but they're not quite as bad as the nonmetals. Again, they're occupying that middle ground between the two extremes. Metals are excellent conductors of heat and electricity. If you think about the pots and pans that you have at home, they're all made of metals because the metal's going to be able to conduct heat. Nonmetals are insulators. Most of them tend to be very, very poor conductors of heat and electricity. Metalloids, educated guess? Yeah, there are semiconductors. If you think about computer chips, they're made out of silicon. Silicon is a metalloid. So they're not as conductive as metals, but they're definitely not insulators, and they've got applications in different technologies. And finally, metals tend to be shiny. We call that lustrous. Our nonmetals, they are lackluster. And our metalloids, it really depends on the specific element. Some of them look a little bit more metallic, some of them are dull or lackluster, like the nonmetals. It really is a case-by-case basis. These are some general properties. What's the first thing you notice as you look at those solutions? Hopefully it's the idea that they're very brightly colored. We're going to spend most of the time focusing on the S and P blocks, groups 1, 2, 13 through 18. This is the one thing I'd like you to know about our transition metals. Transition metals are that D block of elements that chunk group 3 through 12 in the periodic table. When they form compounds, so when they react usually with a nonmetal or a polyatomic anion to form an ionic compound, they tend to be brightly colored. Like this looks like potassium permanganate, and manganese is present. This is probably a cobalt-containing compound. My guess is that one of these two, this blue or this green, or maybe both of them, contain copper. This looks like it might contain iron. So our transition metals are going to produce some really brightly colored compounds. All right, chemists, that wraps it up for today. Thank you so much for tuning in, and I hope you found this helpful.